Earth's magnetic field exerts a force of 1.4 times 10 to the power of negative 5 Newton on a 0.045 meter segment of wire in a truck motor. The motor wire is positioned at an angle of 18 degrees to Earth's magnetic field, which has a magnitude of 5.3 times 10 to the power of negative 5 Tesla at the truck's location. Calculate the current in the wire. So we need to find out the electric current using the magnetic force and magnetic field strength. F equals to B I L sine theta. F is the 1.4 times 10 to the power of negative 5. B is 5.3 times 10 to the power of negative 5. I is not given. L is 0.045 sine 18. So let's multiply all these numbers first. 5.3 times 10 to the power of negative 5 times 0.045 times sine 18. That's going to give me 7.37 times 10 to the power of negative 7 I equals to 1.4 times 10 to the power of negative 5. So I will be 1.4 times 10 to the power of negative 5 divided by 7.37 times 10 to the power of negative 7. Which is going to be 19 ampere. So that's how we calculate the electric current in a wire using the information we have from magnetic field strength and magnetic force. Now in next example, an electrical cord in a lamp carries a current of 1.5 ampere. A 5.7 centimeter segment of the cord, so L is 5.7 centimeter, is tilted at a right angle to Earth's magnetic field. Right angle means theta is 90 degrees. The segment experiences a force of 5.7 times 10 to the power of negative 6 Newton magnetic force due to Earth's magnetic field. Calculate the magnitude of Earth's magnetic field around the lamp. It means that we need to find the value of B, magnetic field around the lamp. Again, we use the same formula, F equals to B I L sine theta. F is given, B is not given, I is given, L is given, sine theta is given. So B will be equal to F divided by I L sine theta. F is 5.7 times 10 to the power of negative 6 divided by I, which is 1.5. L is 5.7 divided by 100 times sine 90 degrees. So when you calculate it, the answer is going to be 6.67 times 10 to the power of negative 5, and the unit for magnetic field strength is Tesla. So that's how we find out the magnetic field strength using the information we have regarding magnetic force, electric current, and length of wire. Now in next example, a current is carried by a straight conductor in a magnetic field of 1.4 Tesla. The conductor is perpendicular to the magnetic field, and the conductor is 2.3 meters long. And magnetic field exerts 1.8 Newton force on it. So let's write down the information. B, which is magnetic field strength, is 1.4 Tesla. The conductor is 2.3 meters long. Force is 1.8 Newton. And the direction is the angle between magnetic field and electric current is 90 degrees because it says perpendicular. Part A, it says calculate the current. So you know the formula. F equals to B I L sine theta. This one is given. F is given. B is given. L is given. We can find out the value of I. So I will be F divided by B L sine theta. So F is 1.8 divided by 1.4, 2.3 times 1. That's going to give me 0.56 ampere. This is the electric current in terms of ampere. Part B, it says, what is the angle between the conductor and magnetic field when the magnetic force is maximum? It is going to be maximum when sine theta equals to 1, because sine theta is changing from -1 to 1. We cannot have negative number for this case, so sine theta is going to be from 0 to 1. So maximum value is 1. It means that theta must be 90 degrees. So this is the angle between conductor and the magnetic field when the magnetic force is at maximum. Now in next example, it says a 120 millimeter segment of wire. So length is 120 millimeter. We need to convert it to meters. So we divide it by 1,000. It's going to be 0.12 meters. We don't need to use calculator. Has a mass of 0.026 kilograms. The segment of wire is oriented at a 45 degrees angle to a uniform magnetic field. The strength of the magnetic field is 0.4 Tesla. Some typo. And the current in the wire segment is 2.3 ampere. Calculate the magnitude of the magnetic force on the wire segment. F equals to B I L sine theta, as we saw it before. B is 0.4, I is 2.3, L is 0.12, sine 45 degrees. That's going to give me 0.078 Newton. Next example, a 2.6 meters wire, so length is 2.6 meter, carries a current of 2.5 ampere. The direction of the conventional current is due west. The strength of Earth's magnetic field at the location of wire is 5 times 10 to the power of -5 Tesla. And the orientation of the field is north. Both the wire and Earth magnetic field are horizontal. What is the magnitude and direction of the Earth magnetic force on wire? So in this case, this is going to be the electric current, I, and B is going to be north. So when we have thumb toward left and four fingers toward north, palm is going to show the into the page. So that's the direction of the magnetic force, and that's how we calculated BIL times sine theta, which is going to be 5 times 10 to the power of -5. I is 2.5, L is 2.6, sine theta is 1 because sine 90. 2.5 times 2.6 is going to be 3.25 times 10 to the power of -4 Newton. Now in part B, it says, what will the force on wire be if the wire is rotated to an angle of 72 degrees with the magnetic field? So it's going to be exactly the same thing, but multiplied by sine 72. So this is going to be 3.25 times 10 to the power of -4 times sine 72. That's going to be 3.1 times 10 to the power of negative 4 Newton. Next example, a long straight wire of length 1.4 meters carries a current of I equals to 3.5 ampere. A magnetic field of magnitude B equals to 1.5 Tesla is directed perpendicular to the wire. Calculate the magnitude of the force on the wire. Again, we need to use the same formula, F equals to B times I times L times sine theta. F, we need to find it. B is given 1.5 Tesla. I is the electric current, that one is given as well, 3.5 ampere. L, length of conductor, which is 1.4 meters. We don't need to convert it to any other unit because it's already in terms of meters. And sine theta, what is the angle? It says perpendicular, so it means that sine 90, which is going to be 1. 1.5 times 3.5 times 1.4, that's going to give me 7.35 Newton. Here it says the current loop in figure below forms a right angle triangle. The loop carries a current I. A uniform magnetic field is directed perpendicular to one angle of the loop, and the angle theta in figure below is 39 degrees. L has a length of 1.2 meters and the magnitude field strength has the magnitude of 1.6 Tesla. Part A, what is the force on the part of the loop parallel to the magnetic field? It means that this side. So F equals to B I L sine theta, and theta is the angle between magnetic field direction and the I direction. In part A it says the parallel part, it means that theta is 0, so sine theta is 0, we can say the force is going to be 0. We don't really need to calculate the rest of it. Part B, it says what is the sum of the forces on the remaining two segments of this loop? It means that we need to find it here and also here. Let's do this part. In this part we have two perpendicular parts. F equals to B I L. Let's call it L prime because this one is L, this one we don't know how much it's going to be. Sine theta, or let's call it theta 1, this one is theta 2. So F will be, B is 1.6, I is not given, just call it I. And then L prime is this one, which is gonna be when we have sine, let's say tan theta equals to opposite divided by adjacent. Opposite is L prime, adjacent is L, so L prime is gonna be L times tan theta, and theta is 39. So it is going to be time L times tan 39. So we have 1.6 times L, which is given, that's 1.2 times tan 39 times L times I, sorry, 1.55 I. That's the force on this side. And we already know sine theta 2 is 90, which is going to be just 1. So that's going to be the magnitude force on this side. Now we need to find out the magnitude force on this side. So F again equals to B times I, which is not given, times, let's say, L double prime. L double prime is going to be the hypotenuse. So I'm going to say cosine 39 degrees equals to adjacent, which is L, or 1.2, divided by the hypotenuse. So hypotenuse equals to 1.2 divided by cosine 39. times sine, the angle between these two is 39. This is going to be like that. So we have 1.6 times I times 1.2, and here sine 39 divided by cosine 39 is going to be tan 39. So it is going to be exactly like the other part. So it is going to be 1.55 I. So it means that the magnetic force on this side and on this side is going to be exactly the same thing.